Good afternoon, everyone. It's my pleasure to welcome you to the stakeholder call to discuss the straw proposal for the Energy Storage Enhancements Initiative. My name is Jimmy Bashar with the ISO Stakeholder Engagement Group. I'm also joined here today by Gabe Murtaugh, the lead for this effort from our policy group. Also George Angelides from our Power Systems Technology Group, and James Lynn from our Settlements Group, who will be presenting for you today. On the next slide, we have our agenda. As is usual, we will be taking questions throughout. To do so, please raise your hand virtually by pressing the raise hand icon. And once you no longer need to comment, please be sure to lower your hand. But if you happen to dial in separately, you would then dial #2 to enter the queue. And we prefer verbal questions, but if we see anything that comes through the chat, we'll be sure to verbalize those for you as well. Today, as you can see, we'll be going over each of these straw proposal categories. And we do have some pretty noteworthy proposals based on all of the input from stakeholders to date. As you can see, we're proposing a new alternative storage model, which George will be discussing here shortly, after which he'll turn it over to Gabe and James to provide context for discussion on the proposed reliability enhancements topic, followed by our proposed co-located enhancements topic that Gabe will conclude with prior to moving on to next steps for today. And on the next slide, we have a typical display of our stakeholder process, as you may also be familiar with. Unlike other ISOs, it's very simple and open to participate. No committee structure, and we use the input provided by stakeholders throughout a series of meetings and written comments solicited throughout each iteration of our proposal development process to carry it forth to our board and EIM governing body authorities for consideration for approval. After which, as you can see, we'll file the tariff changes with FERC prior to going live with those changes and with our stakeholder training and incorporating those changes into our business practice manuals, which is sort of a guide to the tariff, if you will. And on the next slide, lastly, before I hand it over to George, as most recall, the ISO Storage Forum, which we hosted a few weeks ago and which featured a panel of storage experts that discussed more holistically a whole host of market issues in the forefront. That was sort of the last related event to this initiative. Before that, we had led a stakeholder working group that had discussed the potential scope for this effort, after which today, now we're going to discuss the straw proposal that incorporated all of that feedback to date. Also, as a reminder, this call, as most of our calls and webinars, are recorded for stakeholder convenience, allowing those who are unable to attend to listen to recordings after the meetings. It will be publicly available on the initiative webpage following the meeting for a limited time. And with that, I'll hand it over to George.
Thank you, Jimmy. Good afternoon, everybody. This is George Angelides. Can we have the next slide, please? So I'll be walking you through the alternative storage model proposal that we have. And before I go into that, I would like to spend a few minutes reviewing what we have already, the existing resource model that we use for modeling storage resource devices. Next slide, please. So that is the non-generator resource model. We also know it as an NGR. And it's a model that is very flexible. We use it for different purposes. It has different types. One of them is the limited energy storage resource, the LESR type, and that used specifically for modeling energy storage resources and their participation. And this particular implementation of the NGR supports the round-trip efficiency, or we also call it charging efficiency, and also state of charge constraints that make sure that the dispatch of the storage device is feasible with respect to the energy storage requirements to support the awarded commodities and schedules from the market. And a very specific application of this model is for regulation energy management. This is a system that is used specifically for storage resources that provide only regulation, and it's used by our energy management system to essentially maintain a 50% charge for resources that provide regulation, so that theoretically they can provide regulation indefinitely. So this is our existing ESR model. The NGR model, though, it's more general. It's used for multiple other reasons. It has another type we call dispatchable demand response, or DDR. That's used for demand response participation. That's one way demand response can participate in the ISO markets. And it also has a generic form, what we call generic NGR, GNG. That has very specific applications whenever we need a resource that can have an algebraic injection on the grid, meaning it can be either positive or negative, injecting energy on the grid or absorbing energy from the grid. We use it for very specific purposes. Like one example is the overlapping resource aggregation model. And we also use it whenever we want to have modeling of dynamic exports at intertie scheduling points. So essentially, that is used instead of our intertie generator TG model, where you can have a dynamic export in addition to dynamic imports. So I'm making this introduction here to explain that the NGR model, the way it's in existence today, it's much bigger than this, covers many areas. And that is one of the reasons we decided to resolve some of the limitations that the existing model has with respect to modeling storage resources that I will go on next and explain, by building something new. We wanted to minimize risk for touching this model that is used the existing model is used for many purposes, and build something new to accommodate specific needs and requirements for storage resources. Next slide, please. Thank you. So this is an example of the energy bid that we support for the NGR model. It's essentially a continuous model with no discontinuity around zero. It can seamlessly absorb energy from the grid, like charging, and turn around and immediately next interval discharge or produce energy to the grid. Typically, the charging piece and the discharging piece of the energy bid has a gap, what we call the bid spread, that is used by the market to optimize the dispatch of the storage resource across multiple intervals in a time horizon, so that it results in a optimal schedule across the time horizon that results in a profit from participation in the market. What I want to stress here is that this incremental energy bid is in terms of megawatt, in terms of the megawatt schedule of the resource, and it doesn't depend on the stored energy. And this is one of the limitations of this model, which let's go on to the next slide to list them all out. So, as I mentioned, the existing limitation of the NGR model for storage resources is that the incremental energy bid does not really reflect the operating cost if it depends on the state of charge. And we have heard from market participants that the operating costs can be higher when the storage device is either nearly depleted or nearly full charge. So whenever the SOC is near high or low limits, there is a higher operating cost, and with the existing NGR model, you cannot really model that. Another limitation is the fact that sometimes the operating range of the device may depend really on the SOC, specifically when you're near the depleted status of the device, you cannot charge it at the same capacity as at higher, in lower SOC levels. So essentially the negative P-min of the device is a little higher. The same happens when the device discharges and reaches a low SOC. When it's almost fully discharged, the capacity that you can get more energy out of the device could be reduced on its regular Pmax. And then associated with that, the other operating characteristic that is sometimes prevalent on these devices is that the ramp rate, it also depends similarly on the state of charge. The rate of discharge is lower when the device is almost empty, and the rate of charging it is also lower when the device is almost full. So again, you have a potential dependency of the ramp rate on the SoC. And finally, the other limitation that the NGR model has is that, as I mentioned, is a continuous resource model. It has a linear continuous operation from charge to discharge across 0 megawatt without any transition constraints or costs, right? So we wanted to remove these limitations. So that's why we came up with an alternative model. Can we proceed to the next slide, please? So we have a proposal for a new alternative energy resource storage model. We call it the ESR model here for lack of other terms. Let me make myself clear, we're not retiring the NGR model or forcing every participant that is using currently the LESR model, which is part of the NGR model, for participating in the market. They could continue using this model. We're not, we're preserving this model the way it is. We just want to offer another alternative, another modeling alternative that we believe it's better than the NGR model because it will resolve some of the limitations I previously discussed. And the characteristics of this model in that respect are, these are shown here in the slide. We have an incremental energy bid that is not a function of megawatt schedule, but it's a function of the state of charge. So you can actually capture the costs of operation as a dependency of the state of charge, of how much energy is in the device. And to support this across charging and discharging, this model has separate hourly bids for charging and discharging, and we'll go into that a little bit in detail in the next slide. But let's continue here with the other elements that we're introducing for the energy storage resource. We're introducing a dynamic dependency of the upper and lower capacity limits, again, on the state of charge. This is not through a bid. We propose to have register piecewise linear functions for Pmax and Pmin in the master file, with some attenuation when the state of charge is near a high limit or near a low limit. That's our focus. We want to capture that particular operating range that reduces the capacity of the device. And similarly goes for the ramp rate. Instead of having a ramp rate that is a function of the operating schedule in megawatts, we're introducing a ramp rate that would depend on the state of charge, also through a register step function in the master file. That can have up to 4 segments, the same way like we support for existing ramp rate functions as a function of megawatt. And an additional component here, which is a major change to the existing status quo here, we can support charge to discharge transitions. So this model could be nonlinear across 0 megawatts. You could have a transition constraint if it takes time to transition from charge to discharge or from discharge to charge, and we can model transition costs if there are any costs. And this transition cost would be similar to commitment costs that we model for generating resources. There will be a daily transition bid cost for changing operating mode, similar to startup cost, for example, for generator. And we have to register any transition times in the master file. If it takes a time to transition the resource from charge to discharge or vice versa. And also, if there is a limit, if the participant wants for operational reasons to limit the cycles that the device will have in the market from charge to discharge and so on, we can also model a daily transition limit market. And similar to all commitment costs, transition costs would be included in the bid cost recovery for these devices. Let's go in the next slide and describe a little bit the model in more graphical detail. So this is what we propose for the ESR model incremental SOC bids. Okay, so these are incremental energy bids, but they're not in terms of megawatt and in terms of charge. So you can see the axis of X is really an SOC axis. And for convenience here of discussion, I saw it going from right to left, increasing in megawatt hours. So as I said earlier, we support for this model two energy bids, one for charge, one for discharge. The charging bid is shown in this direction. As it increases, as the SOC increases, it's monotonically decreasing. It's like a load bid. You take energy from the grid at a price. And the discharge is in the other direction. As the SOC decreases, the device discharges, the cost is increasing. It's monotonically non-decreasing because we have to still maintain convexity in our model, right? There is a possibility to change the transition from one bid curve to the other whenever you cross 0 megawatts. So if the device transitions from charge to discharge, you have a transition as shown here in this example. In this example, there are 3 consecutive intervals here from T-1 to T+1. And we assume in this example that this device is charging from T-1 to T, so it's building charge. So we're moving from right to left, all right, on that blue curve, which is the bid. And then there's a transition in the next interval from T to T+1, it discharges. So it's moving on the red bid, which is the discharge bid. In the objective function, we model these costs for the bid. The integral under the bid is the cost. So for the charging portion, the light blue shaded area is the negative cost for charging. It's the optimization sees it as a benefit, so it tries to maximize that. Whereas the cost for discharge is the red shaded area. It's the integral out under the discharge bid. Again, you can see that there is a discrete difference in price between the charge and the discharge bid, what we call the bid spread. It has a similar function as is in the NGR model. Essentially, it uses to dispatch the device across intervals in a time horizon so that the price differential that you see across charge and discharge intervals is greater than or equal to that bid spread, and that realizes profit in participating in the market. Maybe this is a good time to stop for questions if there are any. There are any hands up or any participant has questions?
Yeah, looks like there's a few questions in queue. Yeah, there are a few questions in queue. So I will go ahead and unmute their line.
All right.
Caller, your line is unmuted. You may ask your question.
Hi, good afternoon, George. Can you hear me? This is Aditya from Southern California Edison.
Yes, I can hear you.
Hi, thank you. George, actually, if you don't mind, I'll start with the first definitional clarification, just so that I'm not confused to the rest of the presentation. So by convention, state of charge is a percent by dimension. And based on your graph here and what I've seen in the straw proposal, specifically actually in the straw proposal is written in an example, must have at least 5 megawatt hours of state of charge. Based on those two, are you saying that the CAISO is viewing state of charge as energy rather than percent, megawatt hours rather than percent?
It's an alternative way of modeling it. The two are translatable to each other. So you could take these absolute megawatt hours values that you see in this example for the state of charge, and you can say it's really a variation of percentage between the lower and the upper SOC limit that you register in the master file. So if you're at the lower limit, you're fully depleted, you can say you have a 0% charge. If you're at the upper limit, you have 100% charge, and then you have a percentage in between. It's this almost, it's identical, the same way of looking at the same data. Instead of looking at in absolute values, you're looking at relative values. It doesn't really change the model or the way it participates in the market. It's semantics.
Well, thank you. I get the relation, but my point was so that I understand it better, and because it does matter for the math, because percent and megawatt hours clearly aren't the same thing. In case later on you're trying to demonstrate some other benefits. So given what I understand so far, and well, from what I see of your graph, I mean, a lot of stuff there, but the upshot I'm getting is this is still just an incremental energy bid model. It's not really a state of charge model. And yeah, basically the resource is being asked that, hey, according to how your bid curve is, you will discharge or charge, which, I mean, and as I understand is the same thing today. I could be missing stuff, but other than just, and I get it that, the state of charge capacity will be higher for more megawatt hours in the battery. But other than just putting that scale on there, I guess I'm missing how this would not be an incremental energy bidding model.
Okay. Well, it's a good discussion. The market, the way we have it, I mean, the solver that we use, how we solve the market, it's really using incremental energy bids, and this is like your derivative of your cost. It's simulated with piecewise linear stepwise curves here, and the integral of that curve is really the cost. So that's why it's an incremental curve, because its integral is the cost, and we minimize the cost. That's how we represent it. Now, the difference here is instead of having a representation of a cost as a function of megawatts, whether it's positive for discharge or negative for charge, which don't have any relationship with how much charge you have in the device. It really depends on how many megawatts the device is absorbing or producing, which is in the case of batteries for most of the time, it's either Pmax or Pmin, except for those edge cases that we try to cut the corners. So it's not very useful. This one here has an incremental energy bid that it really depends on how much charge is in the device, which is relevant for the battery because you could be at Pmax, but you could be at Pmax at 50% charge, at 80% charge, or at 20% charge. And with the NGR model with an incremental energy bid on megawatts, this is the same cost. But this device could have different costs for operating at this different state of charge level. So it gives you this advantage that you actually can capture potentially more accurately the cost for operating the device across the range of its stored energy. It's different. In concept, it's still an incremental energy bid, but the variability of it's in terms of the stored energy rather than output megawatts.
Thank you, George. Actually, that's a good point you brought up because based on your last graph, as I understand it, should still be megawatt hours and not megawatt, because when resource is deployed, it's not going to be just over megawatts, which will be capacity. It has to be over time. So in my understanding, it should still be megawatt hours deployment, including your graph. I think it was on page 7. You can't just deploy in basically a 0 instant of time. So that's why, again, I'm still seeing the existing NGR as megawatt hour, and even this one is megawatt hour. But I'll leave it at that. I won't hold you back. Thank you. I appreciate it.
Yeah. Yeah, you see the megawatt production over a period of time, and that translates into megawatt hours, but the cost is fixed for a given megawatts. So you can have the same megawatt hour production at the same cost, whereas here, as you change from one interval to the next, you have a change in the charge. So when it charges from T-1 to T, it builds up all this blue shaded energy into the device, and you capture the cost for this operation, which is relevant to going from that SOC at T-1 to that SOC at T, whereas the schedule could be at the negative P-min throughout that range, whereas here you have a variation in cost as the device is building charge. It's a little different. It's also megawatt hours, but the way these megawatt hours are represented in the objective function that we minimize is a little different, has more usability for storage resources. We can have more discussion about that later if you wish.
All right, thank you. We will move to the next caller in queue. Alva, your line is unmuted. You may go ahead.
Thank you. Hello, George. This is Alva from PG&E. The model, especially with your use of the term transition, it seems reminiscent to me of the MSG model. One concern that I wanted to raise, and I wondered how you were thinking about it, is these aren't this transition between different steps in the storage curve aren't changes in the state of equipment like with the MSG model. So there really isn't an actual transition. Maybe at the top of the range there's something like a transition, I don't know, but in general there's no requirement in the way you've got it described here in what's on the screen that these be real transitions. It's essentially you're approximating something about the cost of storing or discharging. And the reason I have this concern is because of the difference between day ahead and real time. I'm concerned that the day ahead model is going to be too aggregate to be able to deal with this in an accurate way. I can see how in the 15, or particularly if it goes to the 5-minute market, but most likely in the 15, you could manage these transitions in a way that's very good and could really capture the needs of participants. But these are all 4-hour batteries, and so I have a hard time understanding how you will formulate this in a way that's usable in the day-ahead market. Would you be willing to just talk about that a little?
That's a very good point, Alva. Yes, this transition doesn't necessarily mean that there is a time to transition. It's the mechanism that the model provides support for having a transition to switch the modeling of the cost from the benefit during charge to cost during discharge, and could be an immediate transition. In real time, it may, depending on the characteristics of the device, there may be a real transition time which may require the device to go through one or more intervals at 0 megawatts to separate the charge with the discharge. If not, it's just continuous, and we just have a hook on the model to tie into the model any possible non-zero transition time and any possible transition costs if there are any. I'm not saying that there are, but if there are, we can model them. Now, because we don't expect these transitions for these devices to be so long as your typical MSG, obviously the day-ahead market, this doesn't have that much significance, because obviously within the hour, you can have full cycling for this device. So I don't expect this transition to be significant in the day-ahead market, but for resources that may need some time to transition, like maybe 5 minutes or 10 minutes, in real time we can model that through these transitions. But for the day-ahead market, I don't expect to have any transition time going from 1 hour to the next.
So you don't expect I mean, the thing I would see is that the day-ahead model would assume one state of charge configuration per hour, and it would have to operate within that configuration in the hour, because that's the way the day-ahead market works. That's my concern.
Correct. It will either be charging or discharging in the given hour, but in the next hour it could be in the other operating mode.
But also, it would also be charging and discharging within a certain range of state of charge.
Depending on the economic schedule as it's determined based on those bids, yes.
So you can only dispatch,
like for example,
within a single configuration.
Yeah. So if you so you see in this example, the resource is having some negative schedule for charging, going from T-1 to T, and then it turns around and discharges going from T to T+1. So the megawatt schedule across those 3 intervals, they reflect the changes in the state of charge of the device based on these economics captured by these bids.
Well, how about this as a question? I want to. I'm sure there are others have questions, but thinking about this 90% or 95% issue that a lot of people have brought up, that when the battery gets up into that high range, you have to reflect a different ramp rate and a different cost. Would the day-ahead market capture that without requiring the battery to be in that configuration for an entire hour? That's kind of my question.
From a modeling perspective, we could. I mean, this is a general model that we propose to be used in all the markets. Obviously, for resources that they have very small time aspects compared to an hour, in the day-ahead market, this becomes less significant, but it becomes significant in the real-time market. So we will have, as I will show in the next few slides, support for dynamic capacity limits and dynamic ramp rates that will depend on the state of charge, and that can be used in all markets.
Okay, thank you, George.
You're welcome. Thanks for your question. Very good.
Look, yeah, I think we have a few more questions in queue, George, if that's good for you.
Absolutely. We want to answer all the questions.
All right, perfect. So the next caller in queue is Matthew. Matthew, your line is unmuted. You may go ahead.
Hey, good afternoon, George. This is Matt Smith from GDS Associates. Can you hear me?
Yes.
Okay, great. Yeah, my question is very similar to Alba's very last question in here. When I looked at this, I saw a great illustration of marginal costs based upon depth of discharge, and seems to capture an example. If I understand it correctly, the lower state of charge may have some higher marginal costs than the upper state of charge in this case. And we've also found very similar situations when we're studying operating data, and we gave some feedback into this process, which suggested some similar methods. And I guess I had a couple questions regarding the average state of charge. Will the average state of charge be one of the parameters here to consider in recovering marginal costs? In other words, will the market be able to understand if an operator has a preference for a certain operating SOC window?
We will discuss later on today in Gabe's section of the presentation what exceptional dispatch an operator may have for storage devices. So I think that's what your question about, if there is a preference, a strong preference from the operator to operate this device in a certain way for reliability. Other than that, the operation is really driven by economics based on the bids that the participant will submit.
For a reliability basis, yeah, I think that would make sense. Also, their degradation may be higher in different windows as well. So there may be a sensitivity.
Which is captured by your bid, right? That's why we propose this model, because it has the ability to essentially express the fact that, when the device is nearly depleted, getting more energy out of it takes, it may have an additional cost, which could be wear and tear or whatever it is. Today, you're actually limited to registering more restrictive limits for your SOC limits in the master file, so that we never dispatch the resource in these operating regions, because you have no way of expressing in the market the additional costs for operating these regions. This model allows you to actually say, well, if you want me to go below 10% on the storage, on the SOC, and deplete the device more, I have an additional cost, and I'm going to show it in my bid. So when the SOC is low for my device going depleted, I have a higher cost. So I'm willing to provide this extra energy, but it has a higher cost. You have the ability to show that here.
Okay, yeah, thanks, George. I think we'll look forward to the next slides and see if that helps put things in perspective for me. Thanks.
You're welcome.
All right, very good. We are moving to the next caller in queue. Perry, your line is unmuted. You may go ahead.
Hey, this is Perry Servideo, GDS Associates. Can you hear me?
We can hear you, Perry.
All right. Hi, George. I wanted to start off by saying that I'm extremely excited that the CAISO is taking these steps to better align the bidding interface for the storage resources to the actual marginal cost that they incur. And equally excited by this particular proposal, and it seems to me like it would be a good way to represent the cost of getting to the lower or the deeper discharges that you would incur on the resource. I had just to make sure I'm understanding it correctly, just sort of conceptual ways I'd like to bounce off you, ways to understand this I'd like to bounce off you. And this might also help with Aditya's questions as well. Is one way to look at this, so because the x-axis is the state of charge, which could be represented as megawatt hours or percentage, is one way to look at this is that essentially this is like a dynamic PQ curve. If I were to try to draw the parallel to how people bid today, it's essentially a PQ curve that changes based on what the current state of charge is. Is that an accurate way to see that?
It's a little different for the storage device. They don't have PQ curves, but the analogy is loosely similar in the fact that in a generator, the PQ curve essentially represents an external characteristic that normally we don't model in the market, that says that the ability for the generator to produce power is really affected by how much reactive power voltage, terminal voltage the generator has. This is something similar loosely. Yeah.
I'm using a term.
Is that?
Yeah. I meant the price quantity curves that existing generators submit. Not that I could see the mix up there.
I see.
But yeah, so you could. Am I understanding it right that it's essentially allowing the resource to have a different price quantity curve that's dependent on their existing or their state of charge at T, the time of dispatch?
Yes, that's what it does. It says that if I have to build this energy into the device, or if I have to take this energy out of the device, this is my cost at the current level of the state of charge. And that's why we have two curves, one for charge, one for discharge, because there's a price bit spread in between.
Okay, so I'm just trying to draw the analogy just to help the understanding then is that with this, if I were to use this this bidding model, or this model, essentially within an hour, my bid my bid for, say, providing 10 megawatts could cost $50 in some intervals in that hour, could cost $100, could cost $500, depending on how I set this curve up. But the market optimization would just know which of those prices to apply based on my state of charge. Is that?
If you're talking about the price, which is the outcome of the market solution, that is still the incremental cost of serving the next increment of load, right? It's still, the LMP doesn't change with this model. It's still the marginal price for serving demand at the location. But the way you drive to that price and how this resource and these bids affect that price, whether it's in the money or out of the money, what we say, is really depending on what is the change of the state of charge across intervals. So you have at the end of an interval and at the beginning of an interval a state of charge, and as the resource charges or discharges within that interval, the state of charge changes, and the change in the state of charge, the cost for that is captured by this incremental state of charge curve. So it's similar in nature with an incremental energy cost, but instead of depending on the change of megawatt schedule, it depends on how much the state of charge changes, whether it's building up or depleting. Yeah.
Okay, I think I got it. Just because the difference between these two SOCs could be translated to a megawatt of dispatch in an interval. Yeah, so that queue could have a higher cost, higher or lower cost throughout the hour, depending on what its current SOC is. Did you guys put any thought?
It's what I mentioned.
Yeah, go ahead.
Yeah, it's what I mentioned earlier, that in the NGR model, for a given megawatt output, you have a given cost based on the bid. But in reality, that cost may be different depending on how much charge is in the device.
Right.
And this is the difference here. You capture that characteristic, that cost characteristic here.
And so NGR model, 10 megawatts may always cost $50 throughout the hour. This model is, hey, 10 megawatts might cost $50 or $100 or $500, depending on where we are on this curve. That's helpful. I was curious what thought you guys had on the number of segments here. One sort of issue I might see is that, I think I read that you're allowing 10 segments per charge, 10 segments per discharge. I just think that at its face, it looks like you're giving these resources 20 segments to play with when you're giving every other resource only 10. Do you guys have any thoughts on that?
It was a proposal, an initial proposal that is compatible with what we have already, because these are two bids that will be submitted in our cyber infrastructure, and we already support 10-segment bids. We have this duality of bids because this resort has duality of operation. It has a charging operation and discharging operation. I don't want to compare it directly with an MSG, but loosely speaking, it's like having an MSG with two operating modes, and we do allow different bids for these two MSG configurations. So you can see that it draws a little bit of a parallel to that.
Yeah, I had that thought too. I'm wondering if you could refresh my memory. Do the MSG resources allow 10 segments per operating region, or is it 10 segments total over all operating regions?
It's 10 segments for each bid, for each configuration.
Okay, for each configuration. Okay. That's helpful, George.
Yeah.
Now my hard question is this. I've mainly focused my time on the red curve, I think, and just conceptually understanding it. For the blue curve, I was wondering, overall, it looks like this is a much better way to model the actual cost that these resources are going to incur. Where I'm slipping up a little bit is I look at the charge curve, and it makes sense that you have essentially a decreasing, stepwise, step function demand curve, which makes sense just economically. But I'm wondering if, from a resource perspective, one that's going to incur charge, what the thought is that these values actually need to be different. Like, when we get to the NPM discussion, people are going to be asking, well, at this, how am I using this charge bid perhaps to exercise market power? And where we go back to then is, well, it should be representing some kind of cost that they're incurring. So I guess, is there a thought yet on that, or is that to be unpacked later on why that it would cost more to charge at lower SOCs than it would at higher SOCs?
So these are all good questions, and I'm sure we will touch upon when we start talking about the market power mitigation, if we get into that detail. Our objective here is to present a model that can accurately, or as accurately as possible, capture the cost characteristics of the operating characteristics of the device. And these are bids, right? And they do reflect more or less the cost of operating the device. And these curves basically say, as you build up energy in the device, this is the charge, right? You're still buying energy from the grid. It's still a demand bid. So, buying more energy from the grid, you want to have a lower price that represents that you're going to buy more energy at lower prices, and this could reflect internal costs for the device. So that's why you have a lower bid price for charging more, right?
Yeah.
And the same way for discharging. I mean, this is the natural way we expect monotonic bids, so that we have convexity to be able to solve the market problem of rising costs overall. Now, if your question is what is an appropriate default energy bid for mitigation, that will be a slightly different discussion, and probably not in this section.
Sure.
There is already
I
a market power mitigation proposal.
Yeah, I might have slipped
So
into
I'm not sure exactly
what
was the question here.
Yeah, no, I was just wondering if there was a basis for, thinking of this as a resource and thinking of this model as a way to accurately represent costs that the resource incurs. What would be why is it, I haven't figured out yet why it costs more to charge at lower levels. I get it. I agree on the economics. Should be a decreasing demand curve, et cetera. You buy more, you spend less. So what I'm hearing though is, we could do some more thinking on that, and it sounds like there might be an opportunity to address that in a market power mitigation discussion.
Yeah, and it depends also on the technology, right? So, I mean, your battery pack in your laptop, if you continuously deplete your laptop, your battery is not going to last very long, right? It actually has a wear and tear on the battery. So this represents a higher cost for operating at a depleted battery state, right? So,
sure.
I mean, this.
Okay.
We're trying to have a model that can capture that.
Yeah, I'm really excited by this model. Look forward to hearing more about your thoughts on the implementation and if it causes havoc in the optimization or not. But at this stage, this is very promising, and I'm glad that CAISO is taking these steps to more accurately model the way these resources incur costs.
Yeah, from a performance standpoint, at least we don't have a proof of concept yet, but there is a certain level of comfort because the existing NGR model already has a binary variable that separates the charging with the discharging state of the device for the main reason of the charging efficiency. So the round trip efficiency, we model it in one of the operating modes, the charging mode, And because of that, the model becomes nonlinear going from charge to discharge. So we had to separate the states with a binary variable. So we already have one. So it's very easy to switch bits from charge to discharge here. So this model does not add any additional performance issues to what we have already for storage resources. So we're feeling confident.
Thanks, George. That's extremely comforting to hear you say that. Thanks for pointing that out.
You're welcome, and thank you for your good words.
All right. We're moving to the next question in queue. Renee, your line is unmuted. You may go ahead.
Hi, this is Renee Steichen from Rev Renewables. I'm curious, and I think you and Perry were just touching on it a bit, but I didn't see in the proposal anything explicitly on multi-interval optimization. Is this supposed to, I guess, how do you think this model would interact with that, or is it just kind of wait and see? Do we think it would increase or decrease the frequency of those occurrences?
Mm-hmm. So it's a very good question, and one that we were expecting actually. The fundamental problem that we have in the real-time market, this is only for the real-time market, is that we are only settling the binding interval. However, the schedule, the optimal schedule for the resource is really derived for the entire time horizon. So it's optimal over the time horizon. And that particular market setup does not sometimes come to terms with the fact that we only settle the first interval, the binding interval. This does not change here with this model. This is still an intertemporal model. As you can see, it works across multiple intervals. The example, you have charging from t-1 to t, discharging from t to t+1. This is just an example. So it really works across a time horizon of multiple intervals because, and here more so because the energy schedule in megawatts, let me put the power schedule, the megawatt schedule that you have for a given interval really depends, it's interdependent on the state of charge at the beginning and at the end of that interval. So this cost here that is captured is by changing the state of charge across an interval. So you have three variables playing all together interrelated. The state of charge at the start of the interval, the megawatt schedule for the resource during the interval, and the state of charge at the end of the interval. All these three are interrelated. You can see that it's intertemporal. So we couldn't have this model for a single interval market. It wouldn't work. It's fundamentally for a multi-interval market because it's the charging and discharging is a time interval across time intervals that you can see it. So we don't expect to have radically different elements in using this model with respect to the issue of having an optimal schedule across a time horizon where we only settle the first binding interval. However, we're introducing several mechanisms for storage resources with ESR4. Constraints like the end of hour SOC constraint, where the participant can actually specify where the device should end up at a given hour in terms of state of charge. And these tools could provide assistance in the market participants to manage the state of charge and mitigate some of the effects that we have seen, which our studies also show that they're not very frequent. We only saw very few cases, and we had presentations that we saw that in few cases that we have observed these scenarios that are problematic. They don't happen all the time. And we also found out that it's only for specific resources, that not all the resources have this problem. So yes, you mentioned it, and I want to also say here that we have a wait-and-see approach on how these new tools that will become available will have an effect on this, and it still remains an issue that we want to observe in the future and see if it requires some mitigation. We'll probably need to design something about it. But at this point, we want to make sure that the tools that are made available that can be used by the participants, and we see how they can be used to put some constraints on how the real-time market could dispatch these resources across multiple intervals.
Yeah, thank you. That's helpful. It's, I think this is a very interesting new model. And, but I guess we're, curious to see how it actually plays out in the market. And it'd be interesting to see some sample scenarios in the future, or, testing it among a few projects to see actually how this would play out for participants. Thank you.
You're welcome.
All right. We are moving to the next caller in queue. I think your line is unmuted. You may go ahead. Caller, your line is unmuted. Please unmute yourself. Your line is unmuted. You may go ahead. Hank McIntosh.
Thanks very much. My question has by now been answered, so that's okay.
All right. Very good. We're moving to the next caller in queue. Caller is Carrie. Carrie, your line is unmuted.
Hi, George. This is Carrie Bentley with the Western Power Trading Forum. Thanks for this presentation. Very interesting. I had a few questions. One, going back to what Alva asked, I don't think you ever directly answered him when he said, will you be constrained to one state of charge range in the day-ahead market? And I assume the answer to that is no. But
depends on the bids. The bids will really tell you what's the allowable movement of the SOC. We always stay within the range of the bid, unless the bid changes across hours and we need to transition from one bid to the next. But for storage resources, there's no issue because the ramp rate is superior. So for the day-ahead market, there's no issue within. From 1 hour to the next, you can be anywhere from any operating state to any operating state.
Okay, good. That's what I assumed. I just wanted to hear it directly. And then will there be any constraints between if you're allowing a transition cost and a transition time, will you constrain the day ahead kind of where you are in real time? So like similar to the MSG model, where if you're in one configuration, you lock in that configuration in the real time. Will there be any similar connection between day ahead and real time for storage?
Storage resources are very flexible, so I don't see any reason why you would have this kind of limitations. The resource could have a day-ahead schedule. It's re-optimizable in real time if you submit a bid, and it could instantly transition potentially from a charge to discharge if the economics dictate so. We're just, as I told Alva, this model, because it already has the mechanics that recognizes the transition, jumping from one bit to another, it also has the hook for us to potentially model any actually non-zero transition times, if there are any, or any transition costs, again, if there are any. So it gives us this ability to have a more general model that can handle transitions. The NGR model does not, right? That doesn't mean that every device has these characteristics. There are batteries that they can switch instantly from charge to discharge, right?
Yeah. Oh, yeah. I was just thinking of all the new long duration storage technologies out there that will have a transition time. So just thinking through whether there would be a constraint between day ahead and real time. It doesn't sound like it. Will there be, and I didn't see this in that paper, just will there be a cost cap or the transition cost? Is there a formula for that?
Yeah. We don't have a formula, of course. This is just a proposal at this point. But as you know, all commitment costs they're expected to be cost-based, right?
Mm-hmm.
Or at least they have a cost-based cap. And if there is going to be a transition cost that we allow in this model, I expect something similar. There will be some sort of a cost-based cap, right?
Yep, I assumed as much. And then last question I had was going back a slide, you said that there would be a daily transition limit functionality. Were you thinking that's just the transition limit would be times it can cross from charge to discharge, or is there the capability to do more of a cycle limit?
They're the same, really. Essentially, you can have a limit to how many daily cycles you're going to have. And we can model it like that. Or you can model it as how many times you can go into a charging mode, but they're really related. It's an additional mechanism that could provide the ability in the day-ahead market and also in the real-time market by extension to limit the cycling of the battery between charge and discharge cycles if there is a certain operational limitation or some prohibitive cost to do that excessively. So you do have the ability through this model to have a constraint that will restrict the cycles within a day to a certain limit so that it doesn't go a lot. But of course, this is also controlled by the bids to a certain extent and all these end-of-hour SOC limits that I mentioned earlier. So you have a good selection of tools here to manage the operation and the economic schedule of these devices.
Mm-hmm. Yeah, I see
is
that.
Just one more.
Yeah, that's helpful. And then actually, one more question did just occur to me. As you get into the upper and lower ends of the state of charge, you also see changes in round trip efficiency. Is that being added to this, or is that not part of this proposal?
Yeah, that's a tough one, Perry, because this is, as I mentioned earlier to Perry, we have a binary variable just because of this charging efficiency, which is a fixed thing. If this were to be made variable, we won't be able to have the performance required to have this model. It's untenable. So I think we have to be, content that we can model a single efficiency. There are other ways that we introduce here in this model to show restrictions when you operate in those marginal state of charge areas, as I'm going to show in the next few slides, which we hope that they will be useful.
Okay, great. I'll wait to listen to those then. Thank you, George.
You're welcome. Thanks, Carrie.
All right. I think that is it for now. There are no additional questions in queue.
All right, very good.
Thanks, Michelle. Sorry, George. I think we had a couple of written questions.
I'm sorry.
Oh, sorry, George. Yeah, I don't want to interrupt. We had a couple of written chat questions. To the extent you can answer them. I'm not sure if you addressed this earlier, George, but we have a question from James Mearns. Sorry, I forgot your last name wrong there. He asks, perhaps this has already been addressed, but how does the proposed model compare to the existing pump storage hydro model? Maybe you can clarify that back on the previous slide that talked about the different types of storage models.
We can stay on this slide. We can stay on this slide, but this really doesn't compare with the pump storage model. There are limitations on the pump storage model that are not here. The pump storage model for the pumping operations is a single operating point. There is no variation. So a pump cannot set a price. It's a single operating point in the pumping mode. Here, when the resource or the device is charging, it's a full bid, full incremental bid, incremental energy bid. So the device can actually set the price while it's charging. Huge difference with the pump storage model. And the pump storage model also, we know that it doesn't support aggregation. This model here, it doesn't have operating characteristics that are very specific to a specific device. You can have multiple devices that could be aggregated and represented with an aggregate model. This requires a little bit more thought, but this is another difference with a pump storage model. I don't think the two can compare in any way.
Yeah, thanks for clarifying, George. That's pretty unique storage model for pumped hydro. And then we have one more chat question before you can continue. I know it's a lot of questions. Thanks, George, for clarifying all of this. To the extent you can answer this, from David Reddy asks, are the majority of the technical issues encountered unique to lithium-ion technology, bulk storage resources, or are they encountered with flow battery technology or other technology types?
So we are always trying to be technology agnostic. We want to have a model that could be used as efficiently as possible, no matter what technology is used. We understand that some technology has specific limitations. To the extent we can model limitations that exist for specific technologies, we try to, but we don't really design a model for a specific technology. And I'm not familiar with all these different storage technologies, so it's not a question that can easily answer other than we didn't have a specific technology in mind when we design and now that we're proposing this model. We basically took comments from the market participants on what kind of limitations exist with the existing storage model. We tried to come up with something to remove or ameliorate as many of these problems as we could.
Great, thanks for clarifying, George. And that's all the questions we have. I know that's almost the end of your section. You have a couple more slides, so hopefully that works well timing-wise.
Yeah, let's go through this few slides. Let's go to the next one. So the other issue we wanted to capture here, it's related again to operating the device near the edges of the state of charge range. So we know that the devices are pretty linear on the state of charge range as long as it doesn't go to the extreme cases of being nearly fully depleted or nearly fully charged. And what we have heard from market participants was that, when the device is nearly fully charged, it becomes less efficient to try to charge it more. Or when it's almost fully depleted, it becomes less efficient trying to get energy, the last energy out of it. And this can be seen as in the fact that the operating range shrinks. The maximum capacity of the resource is reduced when it's nearly depleted, and also on the negative side, on the negative mean, the negative capacity is reduced in absolute sense when you try to push more charge, more energy into the device when it's almost fully charged. So to capture this, in this model we introduce maybe I shouldn't call it dynamic capacity limit. It's dynamic in the optimization, but the characteristic is set up in the master file so that we have it registered, and then the market can use it. Essentially, what we do is we take the feasible region and we cut some corners, so we still have a convex region to work with. So that's why we're not concerned in terms of optimization efficiency. This is not issue for performance. We can do this without binary variables easily. It's multiple constraints that are enforced in the model. So what we propose here is to register in the master file these edge ranges of the state of charge range, which you can have, of course, the SOC min and the SOC max is your your operating range, what you want to potentially operate in, there is always a limit. You don't want to charge more, or you don't want to probably go to zero SOC. There's probably a minimum limit. So these are the absolute minimum, the absolute maximum. But we also want to allow the participants to register, those prime SOC limits that I saw here in this figure, that basically say, when you are discharging the resource and you go and you deplete the resource, you reduce the SOC beyond that SOC min prime, all right? Let's talk percentage. Let's say if 0% is the SOC min and 100% is the SOC max. Let's say that when you're depleting the device and you're reaching the 10% SOC, at that point, taking more energy out of the device is reduced efficiency in capacity. So the capacity of the resources is reduced. It's less than Pmax. So we can model this with a linear attenuation at some slope based on registering this Pmax prime and SOC min prime value. And the same with on the Pmin, that the negative Pmin, it has to be reduced in absolute value, become less negative, if you build charge in the device beyond that SOC max prime. So beyond, let's say, the 90%. So this will give you the ability, when the device is optimally scheduled based on this bits that we saw in the previous slide, if it happens to be operating in these edges of the SOC range, it has a feasible schedule that we don't dispatch at Pmax being at 95%, at 5% SOC if the device cannot discharge at Pmax at this point. Right? So this was one of our concerns. We want to have a model that is producing feasible outcomes. So that's one of the other features. So let's go to the next slide, and then we'll take questions on all of those if there are any. Next slide, please. Thank you. So the other issue is the ramp rate. So we do support in the market today dynamic ramp rates for generating resources and even for LESR. I believe we have two segments for LESR, one for charging, one for discharging. So you can say that over the operating range of the device, the ramp rate can change. But here we want to push it a little bit further. So you can have multiple segments, up to 4. We support for generating resources 4 segments for a dynamic ramp rate. But what is different here is we structure this ramp rate not as a function again of megawatts, but as a function of megawatt hours, a function of the SOC. And it can be in absolute megawatt hours or percentage SOC. This is again, as I said, semantics. One converts to the other. So that's why you see in this first curve here, which is the ramp rate function, which is a stepwise function, and this one does not have to be monotonic function. It can be any kind of ramp rate. So you can have reduced ramp rate on the edges of the SOC. In this example, between 0 and 20%, and between 80% and 100% of SOC, and then a higher ramp rate for the normal range of the SOC that you're operating. This is the ability. This model provides this ability to capture reduced rate of charge and discharge at the edges of the SOC range. And it's a little bit of an exercise here to show you how this ramp rate function translates to a ramp capability function, which is what the market is actually using to restrict the schedules of the resource across intervals to make sure that the ramp feasible. And it depends on the market. So I show here for a real-time dispatch, the 5-minute ramp capability and how it's derived from this function. I'm not going to go through this. I mean, if somebody is interested, they can use this figure to really calculate how this ramp capability function from a stepwise. You can go to a piecewise linear curve for the ramp capability function. And essentially, we use this to restrict or to constrain, I should say, the commodities that are awarded for the device. And I mean all commodities. The energy schedule, ancillary services awards for the real-time market, also the flexible ramp product. For the day-ahead market enhancer will be the imbalance reserve. Okay, so all of these products are constrained with this ramp capability curves. Make sure that the device has the ramp capability to make all of these services, schedules, and awards available or deliverable. I think this may have been my last slide. Can we check to see if this is the last slide? Thank you. Yeah. Okay. So I'll stop here and I'll see if there are any questions on these last few slides or on anything else that we discussed in this section of the presentation.
We do have a couple of questions in queue. Call, your line is unmuted. You may go ahead.
Hi, this is Wei Zhou from ACE. Can you hear me?
Yes.
Hey, George. Thank you. So this is, I think, probably a previous discussion. I didn't get a chance to ask the question, and I joined the WebEx later, so I'm not sure if you already addressed the question. So the questions are very simple. I think I'm trying to use maybe, kind of the, I guess this question probably relate to or kind of similar to the question Perry asked. He's asking more from a market power mitigation perspective. To me, it's more from, marginal cost perspective. But I think this model, the new model, like ESR model, has some attractive attributes, like you model SOC explicitly and you address like a P-min, P-max, some difficulty today. So I think that's very attractive. But I want to understand the model a little bit better in terms of fundamental design of it. Say if we have a gas unit, because the heat rate is changing from 0 megawatts to your Pmax, so you could construct your B curve based on your marginal heat rate. You put the B curve, based on gas price and your heat rate, right? Now, if you look at it from that perspective for this energy storage resource, you're trying to say, okay, the energy storage resource could have a SOC state of charge from 0% to 100%. I think you got issues around 0% when the battery is empty, and you also got issues around, when the battery is full, so the wrap rate could be different. I think, and this model will address those issues better. But from a cost perspective, for SOC from 0% to 100%, I think your proposal would allow B prices, different B price at a different SOC. I think that may be great, but I'm trying to understand what is the marginal cost impact of that. Is that design still consistent with the marginal cost? So what's the different cost you would bid at a different SOC? Say if the battery at 30% versus a battery is at 40% of state of charge, and you have two different bid prices or two sets of the bid prices for each, and what are the consideration you're going to have to put them at a different prices, bid prices, when at a different SOCs. I think I just want to fundamentally understand it, the proposal a little bit better. So if we can, elaborate on that, that'd be great.
Yeah, your question is on price formation and how the marginal price relates to the bid for as it's used for this resource. Now, as I mentioned earlier, this device can actually set the price both while charging or while discharging. Now, how you can picture this is, as I mentioned in answer to another participant, there are three variables that are related. The state of charge at the beginning of the interval, the megawatt schedule during the interval, and the state of charge at the end of the interval. These are all interrelated. If you have a cost for changing the state of charge from the beginning to the end of the interval, that translates to a cost for operating at a certain megawatt for this particular SOC range. And that cost is what is used in the market to schedule the resource optimally in terms of its state of charge changes across intervals. So it is possible that this resource is marginal, providing energy to the grid when it's discharging, or buying energy from the grid when it's charging, and setting the marginal price, which will match its SOC incremental charging or discharging bit at that point in time. So there's a direct relationship between the bids and the marginal price when the resource is operating marginally, which means, let's say, somewhere intermediate in a segment, not at the edge or at the beginning or end of a bid segment, right? That's when it's marginal. Does that help a little bit the question you had in terms of getting to an answer?
Judge, it helps a little bit, but I think fundamentally I try to understand. I think what you explained, if I understand your explanation right, is that the resource could set a market price, and when it set a market price is marginal, I fully get that. But I was trying to think, just say two identical resources, right? One is 30% SOC, the other is a 40% SOC. Do you or does the CAISO expect the two resources to bid differently, or identical resources? But do you expect them to be the same bid price?
I don't expect them to be the same because they're different SEs, and different SEs have different expectations about what they want to take out from their participation in the market. You see, for storage resources, we did mention that there is a cost for operating on those edge regions of the SOC because of wear and tear that, so reduces the life of the equipment, for example, things like that. However, if you're operating in the nominal SOC range, there may be very little cost per se to operate the device, and then your bids really across intervals from charge to discharge and vice versa. So essentially, what we call the bid spread is really your bid into the market for taking energy in one interval and giving it back to the grid in another interval and making a profit. So when it comes to storage devices, the question of what is the actual cost of the device is a little bit hard to answer, and maybe you should be talking to participants that are operating these devices and bidding them in the market. We know already, and we have discussed this in the past, and we saw it, that how the market schedules these devices is really to maximize the revenue for these devices based on their bid spread across intervals in the time horizon. So it's the bid spread that really shows that it's the equivalent of bidding into the market. So you can see individual charge bids, individual discharge bids, but really what matters for the market optimization is really your bid spread between those two. That's what the market is scheduling optimally the device for. So this is also perhaps relevant when we start talking about market power mitigation. Is it the bid, the specific bid we want to mitigate, or is it the bid spread between bids that we want to mitigate, and what the mitigated bid spread should be? So these are all questions that we cannot answer in a few minutes or even a few hours for that matter. Well, but it's it's good to think about, when we go into concepts of market power mitigation to understand what do we mean by cost for these devices, what do we mean by bid and participation, and what is a mitigated bid supposed to be, and things like that. So it's not easy to answer them on the spot.
Okay, thank you, George. That helps a lot. So maybe a final question, if we don't mind. So I think a lot of costs for any storage resource are opportunity costs. I think you mentioned wear and tear cost. Definitely, there are those costs as well. So if we just look at the opportunity cost, will there be different opportunity costs for different set of charge?
Also a difficult question to answer, Wei, because it also depends on what other commodities are awarded. You see, the term opportunity cost could mean different things and at different circumstances. So there are opportunity costs that are time-driven. You have an opportunity cost in a certain time period against another time period. And this is very relevant for storage devices. If you're going to hold your energy in this time period and dispatch it in a later time period, there might be an opportunity cost for holding your energy in the current time period versus future time period. But there are also opportunity costs. The traditional opportunity costs are in the same time period. When you reserve capacity and you don't dispatch it as energy, then there might be an opportunity cost for that reserve capacity because it's not paid the LMP, it's paid the capacity price, but there might be an opportunity cost for it, which in a well-functioning market should be captured by the capacity cost of the product. And this is what happens in our market. We do that. So there could be, yes, different opportunity costs even for identical devices, depending on in which services they participate and which awards are awarded, right? So.
Okay, thank you very much. Thank you for your explanation. I will think about it. Thanks.
So,
right,
operator, we have time for 2 more questions. I'm told we have to move on.
Caller,
so
your line is unmuted. Caller, your line is unmuted. You may go ahead.
Hi, Judge. This is Rahul from AES. Can you hear me?
Yes, I can hear you, Rahul.
Judge, 2 questions. First, the ramp rate function that you mentioned, is that going to be only for the new ESR type, or that will also be included for NGR?
So, as I mentioned in the beginning of this presentation, we do not intend to change the NGR model. We do not want to introduce risk on the existing model because it's used for a lot more than storage resources. We do have a ramp rate constraint, a ramp capability constraint for the existing NGR model based on its ramp rate function that can have 2 segments. But this is a ramp rate as a function of megawatts. So we're introducing here a ramp rate function as a function of the SOC, and we envision that we can have up to 4 segments like what we have for the dynamic ramp rates for generating resources. So yes, this is a feature uniquely designed for this model, specifically the ramp rate as a function of the SOC.
Okay. Second follow-up question, maybe obvious. Will the new model also support ancillary services and include the impact of the changing ramp rate?
I wouldn't call it a model if it wouldn't support ancillary service. Of course it will. And yes, the ramp capability constraints will constrain energy and ancillary service awards and flexible ramp awards in real time or imbalance reserve awards and day ahead market enhancements. Yes, of course.
So there will be some similar feature like the simplified ramping that would impact this model?
Yes, it will actually look exactly the same, but instead of being in terms of megawatt, it's going to be in terms of megawatt hours for the SOC in the device. So
thank you.
The function is same, but the variable that the constraints formulated with is basically the SOC, not the megawatt schedule.
Thank you, George.
You're welcome.
All right, and we have
Maybe
one final question. Yes, you have one final question in queue. Caller, your line is unmuted. You may go ahead.
Yes, hi, Siddhartha from LCG Consulting. Hi, George.
Yes, hi, Siddhartha.
Let's see, I'll try to make this one quick because I know everybody's going to go to the next topic. I think it feels nice to me, this whole proposal from, when I think about it from the real time, maybe, it all kind of makes sense. It all pieces together nicely, especially when you think about the state of charge. But I'm going to probably give away some of my ignorance here. So for those, I'm thinking when you're solving those real-time problems, that state of charge is actually coming, at that moment when you're solving that real-time one increment problem. But then when I kind of think about it in terms of the day ahead, I get a little confused. I was hoping you could help me out with that. So it's kind of like,
sure.
Even just from the very start, like the hour zero, what are you assuming the state of charge is, and then I guess you have to do a multi-interval solution, so you kind of have to know what those state of charge is going through there. Does that P min, we're calling it the dynamic capacity, figure in when when you're doing your efficiency calculations for that state of charge? And then also, I think it's sort of like, similar to Carrie and I think Alva's question about the, I think of it more as a state. If you have all these different bid curves and you're, there's all these different possibilities for a state of that battery. If you have a 2-hour lithium-ion battery, and you could imagine over the 5 minutes, within an hour you might be in 5 different states or something. But for the day ahead, you can only be in a total of 24 states the whole day. I don't know. Is that a similar kind of a?
That's true.
So.
Yeah, it's the effect of the granularity that you have in the market. Essentially, when we calculate schedules in the market, the schedule is for the time interval that you have in the market. So for a 5-minute dispatch, you have a 5-minute schedule, and it can change in the next 5 minutes. So you can have a change of state from charge to discharge across 5-minute intervals. For the day-ahead market, the schedule's for the entire hour. So you're either charging or discharging for the entire hour. You can change in the next hour. So fundamentally, the problem is not different. All the markets are the same. It's the time duration of the interval that makes a difference. And, you always start from an SOC, right? You have an initial point, even in real time. Now, in real time, it's easy because you have telemetry. At least for RTD, you know where to start. You have telemetry to tell you where the device is. In other markets, you have to start from either the previous market solution. In the day ahead, we do have an initial condition for the day ahead market. Now, coming for storage, we have to assume an initial condition, or we can have the participant tell us what initial condition they will have by extrapolating what's going to be their SOC at the end of the real-time market in the current day for tomorrow. But these are generic problems for any market optimization that you'll have. You have to start from an initial condition. Once you start from that initial condition, now the state of charge is a variable, as is the energy schedule in your model, your optimization model. And in the NGR, you have the bit in terms of the megawatts. So you can say that the control variable is the energy schedule, and the SOC, the state of charge, is a dependent variable because it depends on what the energy schedule is. Here in this model, those roles are reversed. You have the bid is on the SOC change, on the delta SOC. So you can say the SOC is the control variable, and the energy schedule is the dependent variable. But these are semantics. In the optimization, they're all variables. They're all co-optimized based on some cost function. So at the high level, there's no real difference. You you solve the problem on different variables with the cost represented on different variables. But what you get out of it is that this particular model, because we're choosing the SOC to be the control variable, gives you more control representing the costs and the operating characteristics and limitations as a function of that particular variable, state of charge. The megawatt schedule, as I said earlier in this presentation here in this discussion, is not so relevant for the batteries. The batteries they go from Pmin to Pmax, right? They have such a high ramp rate that, if it's in the money for discharging, Pmax, that's your schedule. If it's in the money for charging, Pmin, that's your schedule. So really having a bit and ramp rate and everything as a function of megawatt doesn't really make sense. What makes sense to have these functions as a function of the state of charge. That's the real variable here.
Got it. And then, so I guess that the difference is that in the real time, you kind of know what the state of charge is. In the day ahead, you're sort of responsible for maintaining that state of charge for the 24 hours. And then for that dynamic capacity, is there any sense, does it play in there? Like if you think of, okay, if you put in, 1 megawatt, you get 0.85 megawatts out, that efficient round trip efficiency or whatever. Does that dynamic capacity doesn't affect that efficiency, does it?
No, they're going into different parts of the model, right? What I mentioned earlier, the interrelationship between the energy schedule, the state of charge at the beginning, and the state of charge at the end of the interval. You don't have the efficiency if it's discharging. You assume 100% efficiency for discharging. But to capture the round trip efficiency, if the megawatt schedule is negative, which means that the resource is building energy, is charging, now in this relationship between the state of charge and the megawatt schedule, we factor in this charging efficiency that says that, if I have a 1 megawatt of minus 1 megawatt for charging a resource over an hour, then I'm going to build 1 megawatt hour into the device, but not really, because it has a 90% charging efficiency, which means that out of that 1 megawatt hour that you put in the device, you have a 10% lost energy somewhere, so that you will only get 0.9 megawatts out when you discharge it. And we model that with a 90% charging efficiency. This is in the relationship between the state of charge and the energy schedule. That appears only when you charge, not when you discharge.
I think I understood. I mean, I get that, but that doesn't matter. There's no sense that it would take, you'd get your 0.9 if it was state of charge was at one place, but you'd get 0.8 if it was at a different place.
Across intervals, you can see that if you start with a 0 state of charge, and you're charging with a 90% efficiency, let's say for the first part of the day, you will see that if you're discharging the next part of the day down to, again, an SOC of 0, you will see less energy discharged, 90% of it, from what was consumed to charge. You will see that in the schedule. And that also indirectly affects the marginal cost of operation, right? What we said earlier about the price spread, the bid spread. Mm-hmm. The charging efficiency affects the true bid spread. There's the effective bid spread takes into account the charging efficiency, the fact that not every megawatt hour you put in the device, you're going to get it out. You're going to get less. And that reduces the profit as is described or represented by the bid spread. Because we optimize that too. It's part of the optimization. In the sense that if your bid spread is $10 and you don't see your device being scheduled optimally, whereas the LMP difference is $10 across the periods, guess why? Because there's a charging efficiency that requires more than $10 difference to be schedule the device to be in the money. So the optimization model takes care of that.
Thanks, George. Thanks, Siddharth, for your question. I hate to cut you off, but we
That's
do
fine.
actually have a little pinch for time. Thanks very much for your time and answering all the questions, George. And with that, I'll hand it over to Gabe.
You're very welcome. Thank you.
Thanks, Jimmy. Thank you for that presentation, George. We certainly appreciate you introducing this new model and fielding those questions. I do think I know we're a little bit over time, but I do think it's important that we spend time on the new model. I think probably of everything that we're going to discuss, that's probably the most challenging conceptually. And I think that area of design will be the part that we probably need to think the most about. So I think that's time well spent. And I think the questions were excellent as well. Maybe we could advance the next slide. This section of both the presentation and the paper had to do with reliability issues that the ISO has identified that change as we get deeper and deeper penetrations of storage resources on our system. These are certainly all issues that we, the California ISO, and specifically the operations team here at the ISO, feel are critical to address now, as we have something a little north of 2,000 megawatts of installed storage capacity on our system, and we're expecting thousands of more megawatts in the next few years. At the same time, we need to maintain reliability. I don't think necessarily for any of these specific proposals, at this point of the policy process that we're locked into moving forward with anything that we've written. But we do need to develop solutions to these problems, and I think there could be, a myriad of ways to do this. These are sort of our first attempts at formulating what those solutions might look like, given the conversations that we've had with stakeholders through this initiative and in the past. So with that in mind, I'll walk through them, and I think these naturally break down into three different sections. So, and it's broken down in the same three sections in the paper. So I'll pause after each of these sections for questions. I will be mindful of the time, so we may only have time for 2 or 3 questions. Obviously, we want to hear about these changes or potential changes in the comments. And if market participants have other ideas about potential ways to solve the underlying issues, obviously we'd like to hear about those as well. So with that in mind, the first thing that we flag are concerns around ancillary services and operating storage resources to provide ancillary services, specifically the lithium-ion batteries, the 4-hour duration batteries that we have on our system today. What we've seen, and this is from actual operational evidence here at the ISO, is that storage resources today can be scheduled in such a way that could eventually be infeasible. For example, you might get multiple hours of, let's just say, for example, plus or minus 100 megawatt resource being scheduled to provide, let's just say, for example, 100 megawatts of energy in the upward direction and 200 megawatts of regulation in the downward direction. Obviously, that resource could potentially, or will potentially, run out of state of charge, and there won't be any state of charge left for the resource to continue to provide regulation services, even though we may have scheduled them to do that in the day-ahead market. If that resource runs out of regulation in a period of time after the 15-minute market has run and we sort of no longer have the ability to go out and secure additional ancillary services, and prior to the real-time market, the market will run but it just identifies and flags situations where we expect that we don't necessarily have the capacity available for ancillary services that we thought we did. So one of the things that we are planning to do, and this is in addition to the rules that we already have in place, and this, I think we phrased this sort of as a potential proposal and not necessarily a full proposal, but one of the things we've been thinking about is requiring for storage resources an accompanying energy bid with the ability for the ISO to dispatch that resource within that energy bid whenever an ancillary service is awarded. So for example, if you've got that same plus or minus 100 megawatt resource and the resource is awarded 100 megawatts of regulation up, the idea would be that the resource is required to bid in energy from negative 100 megawatts to 0 megawatts, so that if the state of charge were close to depleted, then the ISO could schedule the resource with an energy schedule to charge while it's still providing ancillary services, and it would still have some state of charge via actually being charged in the RTD market or real-time market, so that it can continue to perform and provide ancillary services. Similarly, I think this requirement would work in the opposite direction as well. If the same storage resource was providing 100 megawatts of regulation down, the ISO would require 100 megawatts of bids in the upward direction, so from 0 megawatts to 100 megawatts. That way, if the resource was close to being fully charged, there would be some way through the energy market to discharge the resource through a positive energy signal that could ensure that if we needed the resource to continue to provide ancillary services, we could charge it up so that it would be there and available. I think the next slide gets into exceptional dispatches. So with that, I'm going to pause here and see if we have any questions.
All right. I do not currently see any questions in queue.
Okay. Well, we can always circle back, so that's not a problem. The next concept, and this one is a little bit more complex, is around exceptional dispatch and a specific exceptional dispatch authority that the ISO may need for storage resources. I believe that we've discussed these kinds of requirements previously in this stakeholder initiative, and it's again, this has been something that's been identified by the operations team here at the ISO, and specifically they said, gee, we may need storage resources to be available at particular times in the day. I think I've listed two examples here on this slide. The first example is, you could be in a local area and you may have already experienced one outage on a line or a critical element, and you may want to prepare that local area in the event that another contingency occurs, so that you don't lose reliability. And the only way you might be able to do that in some local areas, and this is already true of some local areas today, is to specifically charge a storage resource or make sure a resource is charged, and then have that resource hold that state of charge for use later in the event that that contingency does occur. Additionally, you might be expecting higher loads. I think here on the slide, we're saying that this could be a system example, but it could also be a local example as well. You're anticipating significant loads later in the day. You don't need the storage resource to discharge right now, but you will need it to discharge later for reliability. So you may specifically require that a storage resource hold state of charge for use later in the day. The idea here is that this would be a new flavor of exceptional dispatch, and this exceptional dispatch would be different than the current exceptional dispatch that we have. The current exceptional dispatch has a target amount of megawatts, and it's a requirement that the resource move and operate to that specific megawatt target. The new exceptional dispatch authority would be, instead of a megawatt target, a megawatt hour target. So once the resource is charged sufficiently to that specific megawatt hour threshold, then this new exceptional dispatch would require that the resource stay at or above that amount of megawatt hours. Obviously, compensation for traditional exceptional dispatches today is bid or better. So you're paid, you know, if we're requiring your resource to provide 100 megawatts to the grid, that resource gets paid at the higher of your bid value into the market or the prevailing market prices. So if actual market prices are higher, you get that value. But if prices are, you know, the exceptional dispatch is uneconomic and your resource is providing energy and it's uneconomic to do so per your bids, you get paid the bid price instead of the prevailing LMP price. That storage resources can still get dispatched for traditional exceptional dispatches. So we could, you know, the ISO operations team could tell a particular storage resource to generate at a particular megawatt value or to potentially charge a particular megawatt value, and that same bid or better concept does apply for those exceptional dispatches. But you might also be exceptionally dispatched to hold state of charge, and that will have a compensation at a different rate. And I'm going to have, let me make sure James Lynn is online. It looks like he is. But I'm going to have James Lynn walk through how that exceptional dispatch compensation is going to work. James?
Hello, everybody. It's James Lynn, Senior Advisor for Settlements. And we can move to the next slide. As Gabe described, we are looking at creating a new exceptional dispatch type. And this exceptional dispatch type is going to be used by operators if they feel a need to hold a battery at a specific state of charge to resolve concerns or potential concerns in future intervals. Now, in the various discussions previously, stakeholders raised concerns about this, and particularly what would be the lost opportunity cost for that resource having to hold that state of charge and precluding it from participating in the market. So we sat back and we looked at your concerns, and we looked at various different methodologies in which to determine an opportunity cost. What we're going to do is we're going to propose to calculate an opportunity cost for that exceptional dispatch period in which you are told to hold your state of charge. Now, we're going to do is we're going to use a reference price to determine what the opportunity cost is. And I'll get more into what that reference price is in a second. But a good example here is if the operator asks the battery to hold its state of charge for 2 hours in the day ahead market, and the prices are 60 megawatt hours and 100 megawatt hours respectively, and then the battery in essence dispatched later on after the exceptional dispatch period, and that LMP was $80, well, conceptually that battery did not lost an opportunity cost of $20 additional per megawatt for that resource in the interval where the price was $100 per megawatt hour. The second example would be more in real time, where we may have a spike in any given interval of the 1 hour real time dispatch. If we can go to the next slide. So what I started to talk about is a reference price. Now, the ISO we're planning and proposing to is compensating you based upon a specific reference price. Now, this reference price is going to use existing LMP profiles and actual schedules when the resource was dispatched for energy. In other words, when we have gotten out of the exceptional dispatch period, if that battery is dispatched for energy, then that LMP becomes the reference price back to the LMPs within the entire exceptional dispatch period. anytime the LNP within the exceptional dispatch period is higher than that dispatch price, then you will get an opportunity cost compensation for that price differential. Some of the reasons why our rationale in using this reference price is because that battery is actually being compensated for that energy that was held in that battery for that period of time, and therefore when it was finally dispatched, it was economically dispatched, and this would be a good economic reference price to compensate that resource. I'm going to stop here and ask any questions.
Yes, we have a few questions in queue. Caller, your line is unmuted. You may go ahead.
Is that me? I guess it is.
Alva?
Yes, Alva, you can go ahead.
This pertains only tangentially to your part of it. Sorry, James. Just one question on AS and one question on exceptional dispatch, and they're sort of similar actually. On the AS, are there going to be any limitations on how the compensating bid is used by CAISO? And obviously, there's the possibility of opportunity costs being created due to that as well. So I'm just wondering if essentially having that energy bid in place can lead to undercutting. Can the bids be used not to restore capability, but just for pure economics?
I think I think that's a good question, Alva. And I think, starting to frame this again in terms of what the concern is, what we're seeing, and this is from actual operational data, is that these storage resources can be fully encumbered with just their AS schedules. And we know for sure that if that happens, there will be a point where they're either charged up all the way if they're providing reg down, or they're completely discharged, which is more often the case when they're providing reg up. And at some point, these resources just won't be able to provide ancillary services anymore. So I think, to your question, how we are thinking about this currently, and I think this could change, and we're sort of actively soliciting input on it, is we are thinking that we would be requiring bids for these resources, and these resources, these additional bids would be treated just like any other bid. So if indeed the resource was economic, then you'd get dispatch. But if it wasn't economic, you wouldn't necessarily get dispatch. But I think what you could potentially see are uneconomic dispatches to, say, charge a resource that's really, really close to being fully depleted, because we know, the ISO system knows that if it does become fully depleted, we won't be able to meet our ancillary service requirements. But I don't think we've really gone through all the details of how that might work. But I think that's the idea.
Okay, great. It was just one. And actually, when you brought up your example, I realized if you do take a bid economically, it's going to be in the opposite direction of the ancillary service. So your idea would be they would continue to be able to supply the ancillary service during that period of being dispatched, I guess.
Right.
On the exceptional dispatch, what's the plan if the dispatch instruction conflicts with the hold state of charge instruction? That was my question on that one.
Well, it shouldn't. So I think an exceptional dispatch from the ISO should either be for storage resources in the future, if we decide to go down this path, should either be a megawatt instruction or a megawatt hour instruction, and you really can't get both. So if you do receive either one of those exceptional dispatches, that sort of overrides any kind of economic signal you'd be getting from the market. So you'll either be getting an exceptional dispatch or you'll be economically dispatched. And if you are exceptionally dispatched, you'll either be getting a particular megawatt exceptional dispatch, which will be settled exactly the same way it is today, or an exceptional dispatch instruction to hold a particular amount of state of charge, which would have compensation per this additional opportunity cost compensation.
This is just my ignorance, but so that means that if you've got an instruction to exceptionally dispatch to hold your state of charge for the next 3 hours, that's also essentially an instruction to disregard. I mean, there's issues with automatic control and stuff like that, right? So do you just simply disregard 5-minute ADS instructions, or are you guaranteeing that those instructions will be consistent with the exceptional dispatch?
It should be consistent with the exceptional dispatch.
Okay, so you don't have to worry about it, because we have stuff that's essentially being driven automatically because we have too many resources to be able to just move them around manually. So you'd have to assume that the dispatches are not going to conflict, because we wouldn't be able to necessarily head those off. Okay, great, thank you.
Great question, thank you, Alva.
All right, we are moving to the next question in queue. Perry, your line is unmuted. You may go ahead.
Hey, this is Perry Servideo, GDS Associates. My questions, I believe, are for Gabe, not for James. Gabe, a quick one on the AS. I just want to confirm I heard this right. Are you saying that resources with AS awards today, the kite in real time, the KICE was not just forcing a charge on them to get them ready for their AS awards?
Well, it could be the case that it's not possible to force them to charge. So there's no part of the bid curve that, so I think the simplest example is if you're a storage resource, you could today, and you're a plus or minus 100 megawatt resource, you could potentially receive a award for 100 megawatts of regulation up and 100 megawatts of regulation down. At that point, if you did receive that award, the ISO energy awards for the resource can't be anything other than 0. So the market software has no way to actually charge the storage resource today, and that's what we're seeing actually happen to storage resources.
Okay, I didn't quite understand that answer, but I think I get the picture that they can't force the charge whenever it's needed.
Yeah.
Oh, okay. My next question, if you could go to slide, I think it's slide 15, where we start the exceptional dispatch discussion. On this, this seems to me to be an extremely important tool for operations to be able to exceptionally dispatch energy storage resources. And, they should be kind of clamoring for that, I would think. I was wondering today, what do they do today? Are they currently using their current ED tools to hold charge on resources?
I think you might find in some circumstances, I think the first thing is that they are doing a lot of manual work to sort of check on state of charge throughout the day, particularly during, the hot days when conditions are going to be tight and we know we're going to need the storage fleet. So they're doing, and this work is manual, and it takes a lot of effort to sort of, and frankly, it's done by a spreadsheet. So they're running queries, putting data into a spreadsheet, checking the spreadsheet, rechecking the spreadsheet, and it's a really arduous process. But yes, I think to answer your question, if there is a situation where the storage fleet in aggregate might not be charged up at the system level to meet evening, net load peaks, and we know we need storage resources to meet those net load peaks, then the operations team can exceptionally dispatch storage resources to charge today, and they also could potentially exceptionally dispatch storage resources after they are charged to something like 0 megawatts or right around 0 megawatts to sort of hold that state of charge. And if they did that, the compensation would still be done at the same way it's done today, which is bid or better. But when you multiply by 0 megawatts, you effectively get $0 of compensation.
Yeah, I assume there'd be a little bit of compensation because they'd want a little bit of charge there to compensate for the amount that they'll lose over time. But still, probably not enough compensation. So the reason I asked that is that it seems that you already have tariff authority to ask resources to hold charge, to ED them around. And I'm just curious if this is, to me it seems like this is such an important tool that I'm, I don't know if what the plan is, but I don't think that you all need to wait around for developing some kind of hold opportunity cost settlement to just try to build this tool and start using it today. It just seems like a better way to do what you're doing today. Is the idea to try to do that, or is the idea to first try to figure out opportunity cost compensation, which they're not already getting today, even though you can hold them today?
Well, I think we definitely do want to figure out make sure that these resources are getting compensated, because, I think they really out on an opportunity, right? If we say, hey, we need you to hold state of charge, you're basic, even if prices are spiking up to $1,000 or close to $1,000, you're missing out on that. And then if you normally would discharge later in the day and you discharge at $100, yeah, you've lost a lot of that opportunity cost. So I think that is one of the things that we want to address with this part of the proposal.
Yeah, I guess my thought was that, you described a rather arduous process that they need to follow to keep the lights on today when it comes to batteries. My thought just is, don't let the settlement of the thing that you don't settle today hold up development of such a tool. Give them that while we work on the right way to settle the opportunity cost. That's my thought on that. Maybe just and then I had one other question related to the settlement, although I think actually it's just a question for you, Gabe, not for James. I'm just curious. So, I read that there's not going to be a market reoptimization to determine the actual LMP that they missed out on. You'll just kind of use the existing market LNP. I think that's going to tend to overcompensate them on the opportunity costs, because we're talking about, in a lot of instances, maybe lack of additional supply when you would have been dispatching them. I was wondering if you guys are concerned about that, or if you have any thoughts on that. Is this the best option there is right now, or what the thoughts there are?
Yeah, I think it is the best option there is right now. Obviously, the perfect solution would be to say, okay, if you were a storage resource and you could, generate optimally, how would that look? And you'd sort of re-optimize the entire market. You'd come up with a whole new profile of prices. But, as you know, Perry, that's computationally burdensome. It would take a lot of effort to go through that whole process. And if we're starting to talk about, hundreds or potentially thousands of storage resources on our system, we just wouldn't be able to do that for every single resource and every single instance that they're exceptionally dispatched. So I think the idea was that this solution is probably pretty close. I would completely agree with you. There could be instances when these prices are distorted from what they would have been. Obviously, if there's scarcity during the times when we're exceptionally dispatching a storage resource to hold state of charge, you're absolutely right. If that storage resource was generating, we could have seen lower prices during those intervals because you've got more supply. I think, like most proposals that we put out there, this would be something that we would actively monitor if we did see, big differences in prices and what we would have anticipated prices. I think this is something where we could go back and revisit. But I think the way it's proposed right now, this is sort of a good, maybe first place to start with the proposal.
I guess I'd like to just point out I'm kind of concerned with that approach. If we're saying we can't re-optimize yet, we're going to monitor some re-optimization. Just think about that. And I also want to just caution the CAISO to not poo-poo the amount of difference in LMP there could be, especially with 5,000 megawatts of storage coming on the system in the next couple of years, 14,000 megawatts of storage by 2029. This could come out to be an extreme overpayment of opportunity. I just want to caution maybe not jump to a conclusion. There might be something to do. Maybe we can grab the market power mitigation prices or something like that. Just try to maybe think outside the box. I know it's not the simple solution, but the dollars are going to be big here. So that's my caution.
Yeah, and I think if we anticipated or saw evidence that those dollars were big, I think we would certainly step in and take some action there. I like your idea about potentially using market power mitigation runs to determine what these opportunity costs might be. If you've got any other ideas, feel free to shoot me a note, or better still, include them in public comments, and then we can think hard about those internally. But I agree with you. I think we'll continue to think about other solutions as well.
Sure thing. Thousands of megawatts will definitely lower the price. So.
Yeah, agreed. Yeah. Thanks, Barry. Appreciate it.
All right. We are moving to the next question in queue. Joshua, your line is unmuted. You may go ahead.
Thank you. Joshua Arnold, PG&E. Thanks for these slides. I have a couple clarifying questions for James on slide 16. Just want to make sure I understand what you're proposing here so we can give it proper consideration. So under your first example, James, for the day-ahead market 2-hour exceptional dispatch, that $20 per megawatt hours, that would only be for one of the hours, correct? To compensate for the case where the price, the LMP went to $100 per megawatt hour compared to the $80 sell price afterwards?
Yes, you're right, Josh.
Okay, great. And then the other question I have is, how would this work if the exceptional dispatch took things up to the end of a day and we had to look at opportunity cost across days?
So that's one of the things that we have to take into consideration. We are looking at the opportunity to look across days to determine when the next dispatch is, but you are correct. That is one of the limitations we have to take into consideration.
Okay, and just to clarify, the last question is this would be a settlement solution, so we actually would have a fair amount of flexibility in how this could be done.
Yes.
Okay, great. Thank you very much for that.
All right, we are moving to the next question in queue. Carrie, your line is unmuted. You may go ahead.
Hi, this is Carrie Bentley with the Western Power Trading Forum. I'm sorry to bring you back, but going back to slide 14, I realized I was a little confused. It says that storage resources can run out of state of charge, but I thought in the BPM, a constraint was put in to ensure that each resource had a SOC to support at least 30 minutes of the reg award. Is the observation that this change has been insufficient, or can you provide more color on that?
Yeah, yes. Even with that change in place, we're still finding cases when storage resources don't have state of charge in the real-time market. So the constraint that you're thinking about is it is a requirement that storage resources do hold state of charge if they are providing regulation, but that requirement is enforced in the RTPD market, which runs, I think, 37.5 minutes prior to the start of a particular 15-minute interval. And if the resource does not have the state of charge, we can, unaward them the ancillary services and then award ancillary services to other resources if there is availability for ancillary services from other resources. But once you get into so you've got this constraint in the 15-minute market, but then once you get into the 5-minute market, you could be on the last interval of that 15-minute interval in the 5-minute time frame, and that's more than 40 minutes out from when you evaluated whether or not that resource had 50% of what they were awarded for ancillary services. So I think one of the potential ways to solve this is increase that requirement, potentially. But we thought a little bit about that internally as well. I think that's another idea to pursue. But I think what you're getting at, Carrie, is exactly right. You know, there can be circumstances when, and there are circumstances when you meet that requirement, but you still don't have state of charge in the RTD timeframe.
I think it would be interesting, I guess. I know you're saying you may propose this, but as you go forward to dig into that a little bit more, I also wonder if some of this is the result of the day-ahead AS awards where there's no deployment rate assumed. So like you said, you could be awarded, because you can't, the award example you gave before, what would be an infeasible award in 15 minutes, where, you know, you are awarded the full 100 up, 100 down. So I think if that's the issue, then including a deployment rate in the day-ahead market assumption, along with the state of charge constraint, would resolve it, perhaps a little bit more directly than this proposal.
Yeah, that's another avenue that we've thought about internally. I think I'd like to see, you know, if you've got a preference over, you know, the current proposal, expanding the existing requirements, or potentially doing some additional modeling of what we expect, you know, depletion rates for state of charge would be in, say, the day ahead or the RTPD markets. I think we'd like to hear about that in comments, or if you want to email me directly, we can chat about it. But I think that's sort of the feedback that we'd like to solicit from this proposal.
Okay, yeah, will do. Thank you.
Yeah, but thank you for that comment, Carrie. I think that really highlights exactly what we're trying to get at here.
All right, there are no additional questions in queue.
Great. Jimmy, did we have one question come in on the chat?
Hey, Gabe. We had a comment from Dan Williams. Thanks, Dan, again for the comment. He says it seems it would be more important, or it would be important to consider pricing for this product in the scarcity pricing / fast start initiative, or to price them similar to how reserves converted to energy are priced under the arming load framework. Otherwise, it would mute price signals for other resources.
Okay, yeah. Thanks for that comment, Jimmy. I appreciate it. Great. All right. Let's move on then to the final item that we had for reliability. I think we are one more slide, maybe slide 8. Yeah, one more slide 18 maybe. Okay. So today the ISO has a number of tools that we use internally when we're studying needs in local areas for reliability. Specifically, you know, we have the ability to ensure that there are gas resources that are started and available in the event that we're planning for a potential contingency. So say we're thinking about an N-1-1 situation. We know what the load profile is going to be within a particular local area. We know what the import capabilities are in that particular area across the day. So comparing the import capabilities and the total load or the expected load, we can sort of map out a profile of what we think requirements are in terms of internal generation that's necessary to make sure we can reliably operate that local area. Traditionally in the past, we've primarily thought about, do we have enough gas resources started to ensure that we can meet that load profile over the entire course of the day? What we are thinking about here, and again, as we get deeper penetrations of storage and as these storage resources are located in local areas, what we may need to do is not only consider traditional gas resources to make sure they're potentially started, but also think about storage resources and make sure that they have sufficient state of charge to meet the local requirements. And what that could potentially mean is the ISO markets making a trade-off between either starting gas resources and potentially have them sit at PMIN in these local areas, or potentially charging storage resources and making sure they have state of charge in the event that an N-1 or an N-1-1 occurs in those local areas. And as long as either the gas resources are started or the storage resources have sufficient state of charge, we'd be able to operate the grid even if we lost a critical element or even two critical elements within that area, and we'd still be able to maintain reliability. And I think, we've gotten some of the details of how this would work in the paper, but we continue to flesh this out about how we would be doing this. But we would want to specifically call out that we're not, hey, we're not only considering gas resources, but now we're also going to be considering storage resources as well. I do think, similar to some of the other comments and concerns that we've had about reliability, this is something that's already a pressing issue in some local areas, and we do anticipate with the retirement of some of the older gas fleet that this could be a concern in multiple other local areas as well. So with that, I think that wraps up the reliability section. So maybe I'll just pause one more time for questions. Obviously, we can circle back if we need to as well. The final section, the third section, is on the co-located model and improvements we're going to make there. But yeah, I'll pause here for questions first.
All right, we do have one question in queue.
Great.
Perry, your line is unmuted. You may go ahead.
Hey, Gabe, this is Terry Servideo, GDS Associates. I just had a question about what the title of this slide 18, what you mean by internal tools here. Yeah. Is this going to be a constraint in the market, or is it outside of the market? And
yeah, this would be a market-based constraint.
Okay, so it will be a market-based constraint that can impact energy schedules, is how I'm reading this.
Yep.
So will that constraint be priced in the market?
Well, I think that's into the details that we need to work out, but I think our current thinking is that it would be priced.
Okay, because if it's impacting energy schedules, you'd want to see that show up in the energy prices. Okay. Yeah, no, like you said, I'm going to look forward to more details on this. I tried to read it in the paper itself, but always happy to talk about this one. Thanks.
Yeah, I think we certainly could have some additional conversations on this. Okay.
All right, there are no additional questions in queue.
Perfect. Let's go ahead and advance to, I believe, slide 20. Okay. Yeah, co-located enhancements. So these are, so let's go one more slide, please. We've received a lot of feedback about storage resources that have investment tax credit or ITC implications from operating in particular ways. We've heard concerns from resources that have property tax concerns. And I think both of these, both ITC considerations and property taxes, can impact power purchase agreements or other agreements between developers of storage resources and off-takers of those resources, and the terms of the contracts that are struck between the two parties. Specifically, what we're hearing, and these are from contracts that were struck maybe 5 years ago when the projects were first conceived, is that some of these contracts explicitly prohibit co-located storage and renewable resources, prohibit the storage component of those co-located facilities, from ever charging at a higher rate than the energy that's coming off of the renewable resources. I think it's typically referred to as, grid charging versus non-grid charging, where if, let's just say this co-located facility is a storage resource plus a solar resource. If the solar resource is producing at, say, 75 megawatts, as long as the storage resource is charging at 75 megawatts or less, then it's considered to be not grid charging or charging from on-site renewables. The investment tax credit is, and we do go into much more detail about the investment tax credit in the paper, but the investment tax credit is essentially a tax credit that the facility could receive, and the tax credit is bigger the more that the storage resource charges while the on-site renewable is generating. And eventually, if it charges something like 25% over the course of a year, when the on-site renewable isn't generating, I think it loses all of the ITC credit. So there's sort of a cliff there at 25% or something more than 25% grid charging. So from an ISO perspective, we look at these contracts and we're thinking about these contracts and talking with others about them. And I think the thing that kind of strikes us is that these resources are physically capable of providing more services than they're allowed to per their contracts. So you're actually introducing these contractual restrictions on what the actual operations of the resource are. So we're getting less flexibility out of these resources. Specifically, these resources may not be allowed per contract to charge during certain times of the day, although physically they can. And we understand that after, for resources that are subject to the ITC, after that 5-year period when the ITC expires, the operators of these resources fully intend to have the resource bidding in 24/7 and have it, charge if it's economic anytime during the day, whether or not there's solar availability or not. So we really are losing some functionality. I think that's a little bit concerning to us. If we do have some sort of a reliability event in the middle of the night and all of our storage resources are depleted and we can't charge them up, or let's just say we're anticipating a reliability event in the middle of the night, we may not be able to charge storage resources because of these rules if that's the way that these resources are bidding and behaving. Nevertheless, I think we do understand that a lot of these contracts are legacy contracts. They were in place, even before the ISO had much in the way of storage in the system at all. So it's not like the parties striking these contracts had the ability to, or a crystal ball to sort of know how the markets would evolve. I think a preference from the ISO's perspective would be to say, hey, look, we know that even storage resources that do receive ITC can potentially charge from the grid some of the time. And if that charging from the grid was included in prices, at least we could have those bid in economically into the market and reflected in bids. And then if a resource did have to charge and it was a time when there was no energy coming off of the renewable, it would get compensated for that. And then it would be better for us because we'd have the extra operating capability. It would be efficient for the market because you get a market dispatch, and then the resource wouldn't be financially harmed or be financially better off because you're getting paid that additional revenue. So I think that would be our best case solution. But in the wake of that, we are willing to sort of rethink and reevaluate the rules that we have in place for our co-located resources right now, to help better accommodate some resources that do have these investment tax credit or property tax considerations. And I think we can make improvements that'll get the model a little bit closer to the operating rules that or constraints that some of these resources face today. Okay, so let's advance to the next slide, please. Okay, thank you. So what we're thinking about is a mode of operations for co-located resources that can be elected for these resources that have, investment tax credit or property tax credit considerations. And essentially, what we would be doing in our model is ensuring that the dispatch instructions that go out to the storage resources are, when they're charging, are less than or equal to the amount of energy coming off of the total co-located renewable output. We would be collecting some kind of documentation, and that would need to be demonstrated to the ISO to qualify for this alternate operating mode. And once we had that, if it is an investment tax credit situation where it's in place for 5 years, what we would do is we'd have a start date for this resource being in this particular operating mode and an end date for the operating mode. And then once the resource was out of the investment tax credit window, it would sort of revert back to the classic way that co-located resources work without this additional consideration of not charging storage resources beyond what the renewable output of the co-located facility is. We would also be introducing language that would allow storage resources to deviate down in certain circumstances. So when we anticipate that a solar resource is able to produce 75 megawatts, we give an instruction to the solar resource to produce 75 megawatts, and that's equal to the forecast. We give an instruction to the storage resource to charge at 75 megawatts, and we're doing that because we anticipate that that is what the amount of energy coming off of the solar resource will be. That's done in the RTD market. However, the sun, a cloud comes across the sun and you're not able to get the full 75 megawatts for that period. We would allow the storage resource to deviate down and not, let's just say the actual generation off the solar field is 68. We would allow the storage resource to deviate down from the 75 megawatts instructed down to 68 as well to continue to match the solar output. And again, you'd have less instances when you're allowed to do this that deviations between dispatch instructions in the 5-minute market and actual output from the solar resource in actual time, there were differences there and you'd have less deviations. Similar to previous allowances for storage resources to deviate, we would not be doing any sort of unique settlement treatment for these resources. They would be subject to uninstructed deviation if they're not producing at the output that they're instructed to, but it would be a behavior that's at least allowed per the tariff. So if we go on to the next slide, please. Okay, so primarily when there is no curtailment of solar, this would be the mode of operation for these co-located resources under these typical scenarios. However, sometimes when the ISO is curtailing solar across the entire fleet, there could be scenarios when we need the storage resources to be charging, and these would be times, effectively when it's potentially very economic for these resources to charge. So we might have negative prices on our system. We might be actively backing down solar resources, but when we're doing this, these would be the times when we would want to see charging from the storage resource, and not seeing charging from the storage resource could produce reliability concerns where we're, quote unquote, over generating on our system. So these would be particular instances when we will require storage resources to follow dispatch instructions, even though in these cases, there could be circumstances when the storage is charging at a rate higher than the solar is generating because the solar has been specifically asked to back down from a particular generating level because of economics of the system. We're just producing so much solar wind, we need to start backing down those renewables, And in these cases, we'd also require that the storage resources continue to charge so we can get our system balanced as closely as possible. Obviously, these situations are more prevalent in the spring when loads are relatively light. We have a lot of renewables in our system, but they don't necessarily happen a ton of intervals, but it can be prevalent certain times of the year. So with that, I would pause for questions.
All right, we do have a few questions in queue.
Great.
Susan, your line is unmuted. You may go ahead.
Hi, Gabe. Susan Schneider, Phoenix Consulting. First of all, I'm delighted and surprised, but very delighted that you are addressing this issue here. We've been trying to find a home for it, and so we really do appreciate your considering putting this additional flexibility that we've been requesting. So thank you very, very much for doing that. I did have a couple of clarification questions. Let me start with this slide here. When you're talking about economic curtailment of renewable resources, normally economic curtailment means that they have a price bid, and then you're curtailing them pursuant to their bid. So if you have a resource that doesn't have a price bid but has say a self-schedule, and you're just running out of, you've exhausted all the economic bids and now you have to be curtailing self-schedules, is that considered? Usually that's not considered an economic curtailment. It's more of a sort of a reliability type curtailment. But would that be included here, or how does that work?
Yeah, I think yes, it would be included here.
Meaning that if you're curtailing because you've run out of economic bids and now you're curtailing self-schedules, then the storage resources still have to follow their dispatch instructions.
Right, their charging instructions. Yeah.
Okay, we may have a comment on that.
Okay.
I think it doesn't make sense that if you're doing that prices may be negative, for example, and maybe even if you're you've run out of economic bids, meaning even negative price bids, and now you're curtailing anyway. The storage resources may want to charge, so we're going to think about that a little bit.
Right.
But yeah, I think we understand what you're doing. I also wanted to point out in general with respect to this issue that the solar, if you've got solar and storage or wind and storage, the renewable resource has taken a hit already on the QC. So even though you do have less use, in theory, you might have less use of the solar storage resource. You're not double counting. I mean, you're not counting the combined amount as much as it would be if you didn't have the ITC limitation. So it's a little less usable perhaps, but also you're not giving it full credit for RA in that circumstance. And so I think that I wouldn't want the ISO to feel like they're being that somehow this should count for less, that these storage should count for less because you've already taken a hit on the renewable side.
Yeah, and I think many of, obviously there's a large proceeding going on right now at the CPUC that has to do with counting rules and the RA program as a whole. And I think a lot of the counting rules and specifically the rules that the ISO has been advocating for what we're advocating for are resource specific. So I think ideally in the future, if you have a solar plus storage facility and it's co-located and that facility is available, a lot of hours a day and it has high availability, then those would be the resources that we would hope would get more resource adequacy credit than the ones that are saying, well, I'm not really available to charge overnight, which means I might not be available to discharge sometimes because I've run out of state of charge. And I think that would be the idea here. But if you were really strategic and you were bidding your resource in such a way that you had that super high availability and you were always there if the ISO needed to dispatch you, my hope would be that those kinds of resources would count for more resource adequacy credit than resources that weren't there available. And I don't know that I really have a preference for whether that means there's a different counting per se for resources that have ITC or property tax concerns or not. I think if it's done on an individual resource basis, that sort of all comes out in the wash.
Perhaps I'm not 100% sure about that, but you may be right.
Okay.
Can you go back to just one slide on page 21 or slide 21? Okay. When you say that resources must show documentation to qualify for this operating mode, are you talking about that they must demonstrate that they have that contractual restriction?
Correct.
Okay. If they don't have a contractual restriction that way, they may still have the same ITC consideration. So I'm not sure that limiting it only to the contractual to contracts with contractual limitations is exactly addressing the whole problem or the whole issue.
I think that's worthwhile. That's a good point, Susan. Thank you.
Okay. All right. Anyway, thank you very much. That's all I had, but thank you very much for considering this, and we're going to really dig down into it and maybe give you some good comments, hopefully. And then, by the way, thank you for making the comments due on the 12th and not like the 3rd.
Yes, we were talking about that internally, and we thought we'd like to give everybody a nice break, not thinking about storage resources over the holidays. So you are very welcome.
Maybe you could talk to the I people about that.
Yeah, well, I'll try my best.
All right. Thanks so much. Really appreciate it.
No, thank you for those comments, Susan. I appreciate it, and we look forward to continuing to think about this part of the proposal with you guys.
Okay.
All right, we're moving to the next question in queue. Chris, your line is unmuted. You may go ahead.
Hi there. Can you hear me?
Yes. Hey, Chris.
Hey, Gabe. It's Chris Evans, Customized Energy Solutions. I also had a similar question on the kind of RA counting piece of this, and so I think you partially answered it already. It was good to hear your description about how, you'd like to see some, individual, more specific resource by resource consideration on these things. But I think this new proposal, which again, I also think is a really good idea to try to meet the needs of these kind of contractual obligations and concerns related to the ITC. So, I certainly share Susan's views on this being a good first step here. I think the idea of having this kind of operating mode as like a specified master file characteristic or something could be used really easily to help the CPUC differentiate between the resources that do have these restrictions and those that don't. And I would encourage the CAISO to really push for that sort of differentiation to be made, because right now all these resources are actually being discounted and actually I think overly conservatively discounted in their NQC value because of this potential ITC restriction, when some of them are able to do grid charging perhaps.
Right.
And so certainly, I think CAISO understands that, that was the initial QC methodology that the PUC came out with. But I would encourage CAISO to try to push for this as maybe a trigger or mechanism that they can use to do that kind of differentiation and have maybe two separate QC methodologies for those type of resources to better reflect that.
Yeah.
Is the CAISO open to that sort of thing, Gabe? And, do you anticipate that you might be able to, support that kind of thing at the CPUC proceeding?
Yeah, I haven't, I'm sort of doing more of sort of the back end work on that for the ISO, but obviously we've got some point people who are directly involved with the CPUC proceedings. I'll certainly bring that up internally, but I think that's totally reasonable, and I think that's one of the ideas behind tracking this.
Okay, very good. Yeah, I think that's pretty much the extent of what I was really hoping to get at here. But I think it's certainly encouraging that, you guys are trying to get at this piece of it. The only other thing I guess I would kind of mention is that I thought was, a little bit interesting here was the idea of the charging issue that kind of Susan also touched on I think it's on the following slide where you're, saying if you have an economic curtailment and the other resource, the storage resource might want to keep charging or something like that. In those situations, I just would be interested to see if the CAISO has any data about how often that sort of stuff happens. It would be pretty interesting, kind of maybe if you guys could provide a little bit of extra information there to help inform how much this is actually occurring, and if that is the case, then that could support the.
Yeah, that might be a good idea. Okay. Yeah, sure.
All right. Thanks, Gabe. That's all I have.
Thank you, Chris. Appreciate the comments. Maybe we have time for one more comment because we do still have one more slide to go. Operator, is there anybody else in the queue?
Yes, there is. We're going to go to Doug. Doug, your line is unmuted.
Thank you. This is Doug Boccignone from Flynn Resource Consultants. I did want to comment on that slide 22. I think the scenario Susan described where you basically got a self-scheduled VER resource that I'm having a hard time understanding why it would make sense to curtail that particular resource, but then still require the co-located storage to be charged from some other resource that doesn't get curtailed. I mean, the whole. I just want the argument for or the IRS requirement that imposes the ITC restriction is because they grant the tax credit for the storage because it's integral to the overall project. And so, the point is it has to use the output from that co-located renewable portion to charge. So
yeah, I think the first thing I would say is, we're definitely in a proposal stage here, so we've got time to iterate on this and improve on it. Our thinking was, though, that if we're in a situation where across the grid we're backing down all of the renewable generation that we can economically. So, we've got resources, let's just say solar resources are online, they're bidding economically at, minus $10, minus $15, something like that. And we basically exhausted all of those resources. And now we're at a point where we're backing down solar resources that are self-scheduled. What we certainly wouldn't want to do is tell storage resources to charge less, because that would make the situation on the grid even worse if we're already sort of curtailing generation from solar resources and we've got effectively negative generation or load from the storage resources. We wouldn't want to reduce that load, because then we're making our situation worse, where we'd have to curtail even more solar or renewable resources. And I'm not sure that makes a whole lot of sense. But
yeah, maybe I was misinterpreting, because it seemed like what was described in the paper, a straw proposal, was that you could get a dispatch down instruction for the solar resource and not allow the co-located storage to dispatch down, even though the storage resource or the solar resource saying, I want to generate at any price, I'll pay you anything.
Yeah.
That just doesn't make sense.
I think maybe it's just a clarification issue with the paper. And I'll take a look at that, and I'll make sure, in the next version, we've spelled that out a little bit better. But I think the idea is that we would want the storage resources to be charging, probably at their PMIN in intervals when we're curtailing, massively, not only economically, but also self-schedules from all of the renewable resources on the fleet. And I think to Chris's point, we know that this doesn't happen a whole lot. It could potentially happen in the spring, but in the event that it does, the ISO wants the latitude to be able to say, yeah, we really need your storage resource to charge during some instances.
Got it. Thanks. Appreciate
the
explanation.
Really good question. Yeah. So thanks, Doug. And I think hopefully that helps to maybe clarify some of the other questions that parties were asking as well. So I see the time, and we have 8 minutes left. I want to get through at least one more slide and then give Jimmy a couple minutes to wrap up. But if maybe we go to the last slide of my deck, maybe slide 23. I'll go through this one, and then we can pause for questions one more time and maybe take one or two questions, and then we will end the call for today. Obviously, if you still have questions or you want to talk about a specific part of the proposal, you can reach out to George, James, or myself, and we can try to answer those. But the last topic here is something, again, that was brought up by stakeholders as recently as the Hybrid Resources Initiative. And there was sort of this idea that was thrown out there that said, hey, look, you've got this aggregate capability constraint paradigm for co-located resources. We really should think about expanding that idea to pseudo-tied resources. So if you've got a pseudo-tied solar resource with an on-site, also pseudo-tied storage resource, and they've got X numbers of megawatts of transmission rights from their BAA to the California ISO BAA, and that amount of megawatts is less than the aggregate amount of generation. Well, we could use the exact same functionality that we have for co-located resources and apply that to these particular two pseudo-tied resources. And I think all we're saying here is that, yes, we'll update our language on the pseudo-ties. We will allow for that. So you could potentially have, a 100 megawatt solar resource, a 50 megawatt storage resource with 100 megawatts of transmission capability to the ISO. As long as those two resources are both pseudo-ties and they're modeled as pseudo-ties and they're coming from the same balancing authority area, then we can use what we use right now, our aggregate capability constraint, to model that aggregate amount of transmission and make sure that in aggregate the ISO isn't dispatching those two pseudo-tied resources above that transmission capability. So with that, I'll pause for any, maybe one, maybe two questions, and then I'll turn it over to Jimmy to wrap up. Do we have any questions on the line?
I am looking, and I do not see. Oh, there is one question that pops up. Yep, we do have one. Oh, we have two. Okay. Sean, your line is unmuted. You may go ahead.
Hi, thank you so much. On the co-located, is the proposal to simply not penalize charging activities that violate a dispatch schedule? Because I was thinking, like, wouldn't it be elegant if co-located storage had its charging curtailed along with its solar being curtailed so that there was no grid charging implicitly ordered by CAISO? In our case, some of the resources are physically configured to trip offline if grid charging is attempted. So basically, CAISO ordering our solar curtailed would be making an error in assuming that the charging would continue when in fact an unplanned outage would occur instantaneously.
Mm-hmm. Yeah, I think that's a real challenge, right? Because if you've got a storage resource that's modeled in our market, let's just say as a plus or minus 50 megawatt storage resource, and suddenly the sun isn't shining as bright as you thought it was, we do need to see D rates in our system that reflect what the actual capability of the storage resource are. And I think today there's even some, ambiguity about what kind of outages would really qualify for the storage resources, because I believe that most of the outage cards are supposed to reflect physical unavailability and not just, contractual unavailability. So I do think that that's part of, some of the hard angles that we're trying to get at here. But I do think you're right. If we, I think if we take a step back and we think about what this proposal is trying to do, we're trying to say, hey, look, if the ISO thinks and your forecast thinks that your solar resource is only going to be putting off 25 megawatts, I don't want to give a resource that's opting into this model dispatch instructions to charge for more than 25 megawatts. I think for most of the time, we're not going to have any problem meeting those requirements. But I think the catch here, and I think this is where a lot of the questions are coming in, is sometimes the ISO is curtailing renewables across the entire fleet. And sometimes we're doing that for reliability purposes. You know, if we're at a point where we're curtailing everything that's producing as much as we possibly can, and we still basically have too much generation on the system, it would be silly at the same time for us to back down storage resources from charging, which would essentially be a load on our system or a negative generation, because the negative generation actually helps our situation.
Right.
I think there might be some challenges if a resource is not physically capable of doing that, and there's some sort of automatic tripping mechanism that kind of kicks in if the resource tries to produce outside of those bounds. Those might be some certain circumstances that you know we may want to talk with our operations team and with your team about. But I think that is, or it could be, a potential concern for our ISO operations team.
Mm-hmm. Yeah, I worry a little bit about the language being used. I appreciate that being a sort of engineering organization, CAISO prioritizes the physical capabilities above all else. But I don't know, like calling it the contractual capability sounds like, oh, it's just a piece of paper that we, the engineers, don't have to really pay attention to. But these are relationships that counterparties, out of respect for each other, entered into with an understanding. If the ITC got extended, ISO subjecting those counterparties to risks could be a substantial consideration. Maybe we could call it the economic capability of the storage, which does not include grid charging.
Okay.
Because it's not just a piece of paper,
This is a proposal. I think we're still, exploring different options, and we wanted to get this out there as a first attempt. So we'd like to get your feedback and others' feedback on where we're at with this, and from our perspective, how we address the reliability aspects, and from your perspective, the needs that you guys have in terms of contracting and sort of where we are on that side of the house. So I appreciate where you're at, and I think the ISO wants to acknowledge that, but at the same time, we need to balance that with reliability, and I think we'd be open to hearing about how we could do that with this model.
Terrific. Thank you. Yes, and I think it's all very well considered, so thank you.
Well, great. I think that brings us exactly to 4 p.m., so I'm going to cut the questions off there. Like I said, if you have additional questions or comments, you can forward those to me specifically or anybody else in this team. But with that, I will turn it over to Jimmy Bashara to conclude the call for today.
Thanks, Gabe, and thanks again, George and James, and of course, everyone else for your attendance and great questions. If we can advance the next slide, please. The next one, thanks. So as Gabe mentioned and Susan commented on earlier, we're asking for comments on the 12th. And Susan, we did extend the comments to at least the 4th, so hopefully that's better than the 3rd. That's the best the team can do on that one, though, but I appreciate your sentiments on that. Look forward to the commenting templates that we typically post to be available within the next couple of business days for you guys to comment. And you can find the tool there, the link right there. And once more, this was recorded. Look for that to also be posted on the page. And this is a critical part of this initiative with sort of these new items being proposed. So hopefully we were able to focus on what was necessary for today. And we do welcome comments as we further flesh everything out, as all of this is new territory, as Gabe sort of emphasized. So thanks again, everyone. And sorry we weren't able to get to the last couple of comments in the queue, but again, we're looking forward to the written comments. So have a great rest of your day, guys.
That concludes our conference. Thank you for using event services. You may now disconnect.